Hey friends, here we are in chapter 3, first section, 3.1. We're going to solve systems of equations by graphing. So the set of vocabulary that we have should be reviewed from before, but if it's not, let me know so we can discuss it at another time or even more in depth. But systems of equations, what we recall systems of equations being is you have two or more equations in two variables, and you need to figure out not just one variable, but two or more, depending on the number of variables. And the thing about systems of equations is that the number of equations you have needs to match the number of variables or unknowns you have in order to be able to solve it. That's kind of a general rule. So if you have three unknowns, you need three, generally you'll need three equations, okay? So system of equations would be two equations. Sometimes they can be both linear like we have here. We could have x squared plus 2y equals 7 and x to the third power plus 1 equals I don't know why. This could be a system of equation where I'm looking for an x, y, or some variables that these two guys will have in common and a solution that they'll have in common. Consistent, inconsistent, independent, and dependent can be best described down here. Now, these words are used specifically when we're talking about a linear system of equations, so system of linear equations. So we have consistent. I like to think about consistent. Consistent to me means that there is some kind of solution. There is something that these lines have in common. If you notice that we've got two places where we're calling things consistent. It's consistent here when we have one intersection, and it's consistent here where we have infinitely many intersections. So this is this is representing two lines that actually lay on top of each other, therefore they're the same line. So whenever we get a solution, we say that it's consistent when there is some value or many values that satisfy both equations. Inconsistent over here is when we have no solution. So the inconsistent one is when we have parallel lines where there is no intersection between the two lines, no solution that works. Independent here, when I see the word independent, I think, oh, these are two definitely distinct lines. You've got this line and this line. They are independent. They are different. They are distinct. Even though they are consistent at a point, they have a point in common, they are ultimately independent lines. Here, we've got this line, which is dependent, right? This whole situation is dependent. Notice that both lines kind of depend on one another. I don't know where the vocabulary came from in terms of why they use these words, but this is how I'm remembering the connection. So I'll go back through it again really quickly. Consistent means that there's an answer, at least one or an infinitely many. Inconsistent means that there's no answer, there's no pair of variables that's going to work for both of these equations. Independent means that you've got two separate lines that are independent. And dependent means that both of the lines are the same. They depend on one another because you couldn't have one without the other. If one line didn't exist, the other wouldn't because they're the same line. I hope that helps out with the vocabulary. Let's begin with some examples. This first example we have is we're going to solve by graphing. So we're going to look for the solution, the x and y values that satisfy both of these equations, but we're going to do it by graphing. So we know how to graph these guys. We've got a couple ways. We can graph using a table. We can graph using x and y intercepts. We can graph using slope-intercept form of a line. Slope-intercept form is a favorite of mine, so I'm going to do that. And it's also good practice solving for y. So let's do that. So I'm going to take this first equation. Let's call it my pink equation. I'll take the pink equation and I will rewrite it, and I'll rewrite it like this. Y is equal to negative 2x plus 5. Notice I subtracted 2x from both sides of the equation, and I came up with an equivalent equation, but written in a form that's going to be easier for me to graph. The next equation, let's call it the blue one. I'm going to solve in a similar way. I want to get y by itself. When I do that, however, I'm left with a negative y. Notice I'm adding a negative x to both sides. In order to make this a positive y, which is what the formula calls for, I need to basically multiply everything by negative 1. So when I do that, all of the signs change. Y is equal to a positive x minus 1. And so I see that I have my final blue equation there. And let me highlight that. And so now I'm going to just graph. Remembering when we graph linear equations, we start with the y-intercept. When we have it in this form anyway, we start with the y-intercept. We go right to the y-axis. 1, 2, 3, 4, 5. So that's where the first dot of my pink equation is. I go down 2 because the slope is negative 2 over 1, right? We know that that can be written as a fraction as negative 2 over 1. So here's my rise, which is actually a fall, negative 2 over a positive 1, negative 2 over a positive 1. That negative could be shifted down if it suited me, and I could move up 2 and consider going back 1. And what we'd have is the same line. So let me go ahead and give you that linear equation that we got there. Okay, so the line looks something like this. Let's do a similar treatment for the blue equation. So I start at negative 1. My slope is 1 over 1. So I go up 1 over 1, up 1 over 1, up 1 over 1. And things worked out beautifully for me because I can see directly, even though my lines are terrible, I can see directly where those lines intersect. You guys see it? It's right here at 2, positive 1. So the solution set, when you're solving these problems, you're not just looking for one variable value, you're looking for 2. And we're looking for x and y, and we got that. X is equal to 2 when y is equal to 1. Works for both of these equations. Okay, so here's example 2. Break-even point analysis is what that says up there. Let's see. All right, so Travis and his band are planning to record their first CD. The initial startup cost is $1,500, and each CD will cost $4 to produce. Okay, so let's let X be the number of CDs that we're talking about in this problem. So $1,500 plus $4 per CD, and that's going to be Y, the overall cost of what we're talking about. And then we have this other bit. They plan to sell their CDs for $10 each. So each CD that they make, they want to sell it for $10 each. So I want you to think about this. This is what we're going to call the cost equation, right? How much it costs to create the whole situation. And this is going to be the revenue equation, how much money you're bringing in, right? And if this were a business, as we're going to think of it as, you will want to make sure that you break even at the very least. You want to know your break even point. You want to know how many of these things you need to sell. So let me set up my coordinate plane a little bit better. Okay, so I've chosen to make this a first quadrant axis instead. So that's why I highlighted this in red. Our x-axis will be the number of CDs and the y-axis will be the dollars, and we're going to just graph it. So if I graph this purple equation first, I'm going to, which we know is the revenue, the money coming in. We know that the y-intercept is 0. Let me go ahead and slide this down so we have the y-intercept is going to be right here at 0. Will you write for me, my friend? There we go. Y-intercept is at 0 because y is equal to 10x. And then it goes up 10 and over 1. And this is a little hard, but what kind of makes sense is if I choose a number, like, because it's hard to go up over when you've got it labeled in a certain way or numbered in a certain way. So choose one of the numbers. Let's say 100. If I put 100 there, how much money does he bring in with 100 CDs? So if it's $10 a CD, he's going to bring in $1,000. And then I can do the same thing with 200 and see that it's 2,000. And so I get my line doing something like this. And so the next one, we need to graph this guy, but now we have a y-intercept of 1,500, so we're going to start there. So our red equation, maybe that was a mistake, maybe I should use kind of, I think it was pink, whatever. Let's use pink. So our pink equation starts here. That's a little more pink. Our pink equation starts here at 1,500, and our slope is to go up 4 over 1. Again, that's a little tricky to do, so because of the numbering, so let's put 100 in here. If I put 100 in for x, 400 plus 1,500 is 1,900. So when we're at 100, we're at 1,900, and 1,900 is going to be around here. Let's see, that's 20, that's 2,000. This is 1,750. And so we're going to be right there. Let's try another number. If I do 200 and I do 200 times 4, I'm going to end up with 800. And when I do 1,500 minus 800, or I'm sorry, 1500 plus 800. That leaves me up here at 2300, which will be right about here. And then I can continue on with 3000. Not 3,300 rather. 300 times 4 is going to be 1200. 1200 plus 1500 is going to bring us to 2700, right? So then that brings us around right here. 2700 is going to be just below this line, like right there. And so what we have here is our line does this. And the point of intersection, which we're going to investigate, this point is the break-even point. This is when the money that he shells out to create the CDs is less than the money that he's making per CD that he sells, right? So this is when it's worth it if he can get to this value, and we need to figure out what that is. And this is one of the reasons, what I'm going to talk about now is one of the reasons why the next section is so important, because it's hard to figure out what this intersection point is. We need to zoom in a little bit better, draw our graph better to see what that is. So I'm going to go over to Desmos. So here are our graphs graphed here in Desmos, and you know, we can zoom in a little bit maybe, right? You know how Desmos is really just going to give us the answer if we put our finger right here. So what we get is 250. So we could zoom in, I think, and kind of finagle with it. But the fact that we're on a device that can graph it for us shows that our graph is this 250 and 2,500. So that's when he's going to break even. So let's go back to our work. Where's our work? Let's go back to our work, and we're going to write that down. So when 250, let me use a black pen, when 250 CDs are created and sold, he will have made $2,500, right? That should be right there on that line. That's where that should have been. He will make $2,500, and that money would go exactly back to the cost of making it. But from then on, every CD he makes, he is going to gain a profit. So awesome. All right. In example 3, we're going to talk about intersecting lines, and this is really giving us an opportunity to demonstrate our understanding of the words consistent, independent, consistent, and dependent, or inconsistent. If these lines intersect, then we know we've got a consistent dependent situation, especially particularly if the lines are not the same. So let's graph them. The following two equations are how I'd rewrite this in order to graph them easily using slope-intercept form. Here's the first line, or the purple line, and here's the second line, and you can see that they intersect at the point 3, 4. This is consistent and independent. As the title of this example tells us, we're going to be dealing with the same line. So when we solve each equation for y, we see we get the same equation when we solve for y, when we put them in slope-intercept form. So when I graph this, we get these two overlapping lines, which in essence is the same line. We have a consistent but dependent situation. Here in this example, this final example, we're going to talk about parallel lines, and we know that parallel lines don't intersect. Therefore, we're not going to have a situation where they intersect, right? So let's go ahead and make each equation ready for graphing. It should be pretty obvious that these graphs are going to be parallel given the fact that they have the same slope. And so when we graph, we indeed see, and there we have these two parallel lines that don't intersect, and therefore we have an inconsistent system. That's it for us. We'll talk again later. Let me know if you have any questions. The next video is going to be just about solving these guys algebraically using two methods that you're familiar with, substitution and elimination. Bye-bye.